Okay, so starting section 1.2, we're going to play a little bit around with our parent functions and see what happens when we make transformations. A little bit of a review from pre-calculus. We're going to look at maybe reviewing, it'd be really important for you all to keep working on your parent function toolkit. Going through a lot of these functions is going to help you recognize what the general shape of the translated or transformed graphs will be. And it really makes your life a lot easier as you're trying to determine the new graphs. So with example 1, it's asking us to graph y equals f of x plus 1 minus 2. And so a lot of times what I like to point out for myself is I like to see how the function differs from my parent graph. A little bit of a note, I do see that there's an extra plus 1 embedded with the x. And there's also a minus 2 on the outside of the function. So those indicate, looks like there's going to be some shifting going on. And everything refers back to the parent graph, and this is the most basic version of what your graph will be. I'd like to maybe start off with rewriting y in the terms of the parent graph. So if I can do that, that will turn into y equals square root of x plus 1 minus 2. And again, notice the positions of the 1 on the 2 in the function. Look again that the plus 1 is inside the square root, inside the argument, or we call it the radicand. And the minus 2 is outside the square root. So it's kind of helping us think about, okay, what does that mean? So just to go back with the parent graph before we start, we can do a graph, XY chart maybe, to help us out. Maybe I'll do that in green. If this helps you, it'll help with the shift of all the points. I'll do a quick graph on the side, or XY chart. So again, y equals square root of x. So a lot of times if I know I'm going to be plugging in x to the radicand and it's a square root, I'll probably pick some perfect squares. These are some popular ones to start off with. And notice if you were to try to pick a negative number, you would not be able to take a square root of a negative number. You'd have an imaginary, so that's not going to graph on our XY coordinate plane. So if we take the square root of 0, we are going to get 0 back. The square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. So I can graph my parent graph on the graph just to see. And if we're going to plot those points, 0, 0, 1, 1, and 4, 2, looks like we won't need 9, 3 unless we want to extend the graph. But this will help me see the format. I have a square root function, so it's not quite, it's kind of curvy, I guess, but we're not too much exaggerating. So I'll label that as f of x, the parent, just so I keep everything in line. And now back to those extra numbers. Back in pre-calc, we talked about what happens when there is a number on the outside of your actual graph. So I'll kind of point that out and I'll re-highlight that maybe in, I'll keep it green. We'll keep that. Okay. So that extra 2 on the outside indicates that we are going to have a vertical shift, and it's going to be shifted down 2 units. And if we are looking at the 1, and notice it's embedded with the x, it's in the argument or the radicand, that's going to indicate we have a horizontal shift. So we can tell it's 1 unit, but a lot of times with the horizontal shift, we talk about is it left or is it right? And in this case, it's the opposite of what we see. And if you need kind of a little bit of explanation, message me or ask me to explain it. It actually has a lot to do with, it doesn't seem how we think it would be, but it's actually kind of stage left, stage right kind of explanation. Wish I was there in person, I can show you. But let me know if I can explain that. But just so that we know, I like to kind of notate that we have the graph that's going to shift left 1 unit. Sometimes if you can verbalize it, at least you'll have an idea of what to look for. So now in this case, what I can do is take my points from my original parent graph and perform the translations to give me some guidelines so I can make my new function. So if I want to shift a left 1 unit, I take each of those points and I will shift them left, and I'll mark them with little X's so that we can get a good idea. I don't want to commit to drawing a point because I'm not done with my transformation. So I'm shifting left 1 unit, and maybe I'll shift down 2 units at this point. So each of those points that I just drew, we're going to shift down 2 units. And that is going to give us our actual graph for example 1. And so I'll commit to making those ordered pairs. Draw the point over the final shift, and I will use blue to make my curve. And of course, if you kind of know, you can compare this in your TI, you can verify if you know the function. I am a perfectionist sometimes, and so that bothers me that I have a little bit of a curve where I shouldn't have a curve. So let me try this one more time. I'll do the best I can on that. So a little bit, I'm still a little shaky, but we do the best that we can. So that is going to be the y equals square root of x plus 1 minus 2, or if you wanted to rewrite it the way the example started, we can write that on the right. Now the next thing we have to look at is, once we are having a clear graph, it's a little bit nicer to be able to tell what the domain is. And so just like from the beginning of section 1.1, whenever we're looking at the domain, you want to kind of place yourself, your imaginary self, on the x-axis, the far edge. So for example, right here, I'm looking at x equals -5, and you're looking for a picture above or below your x value. And if you don't see a picture, you keep traveling along until you finally find that picture above or below. And it looks like it starts at -1. That x value gives us a picture. So I'll start the domain at -1. And if I keep traveling along the x-axis for all values of x, I still have a picture below for a while. All of a sudden at x equals 3, I have the picture on, so we're still good. And if I go beyond x equals 3, there's a picture above forever and ever and ever for every single x value. So it appears that the domain is -1 to infinity. Remember, infinity always has parentheses, and it looks like the starting point is included, so we're going to use brackets. So similarly, we'll do the same thing for the range. We'll picture ourselves on the y-axis, and we'll start at the very bottom of the y-axis, and whatever's happening at -5 probably also happens at -infinity. So with the range, I'm always looking for a picture to the left or the right, and I don't see anything for -5. And if I keep traveling for all these y values, -4, -3, and decimals in between, I don't see a picture until I hit y equals -2. So it looks like my range is starting at -2. And if I keep traveling along the y-axis for all these different y values, there is going to be a picture to the left or to the right or on. And I know it doesn't look like it when you're kind of around x equals 5, excuse me, y equals 5. But the behavior of the square root function is it looks like it increases forever and ever. So it just increases a little bit slowly. So eventually we would have a picture there. So just kind of looking at that, it appears that our range is from -2 to infinity. And again, -2 is included, so we're going to use brackets. Now, if we're going to talk about whether the function is even, odd, or neither, we can go back to a little bit of the review from section 1.1, and yeah, we can play with plugging negative x for x in if that's something you're interested in. But I prefer symmetry to help me understand this. So when I'm kind of looking at if a function's even, remember it was symmetric about the y-axis, and it does not appear that our function is. We're again, remember, we're looking at the blue function. So I know for sure it's not an even function, so I can rule that out. Odd functions are symmetric about the origin. And when I play around with this, it does not look like it's symmetric about the origin. There'd be some continuation around the negative values of x. So I'm going to rule that out. So the only possibility is we have neither. And if we don't have even or odd, we really don't have symmetry. And the fact that it's a function will never have symmetry about the x-axis. So we can say it's there's none, or sometimes people will say not applicable, however you want to describe that. But don't leave it blank. And if we're looking for intervals of increase and decrease, we're kind of seeing for every single x value, as the x values get bigger, do the y values get bigger. And we don't have to go too far into this. We'll have a little better way to deal with this around chapter 3 in our text. But when I'm just kind of glancing at the function, if I am looking at all the values of x, it looks like the y values are increasing. So it looks like every value on the domain, we are increasing. So I'll look at from -1 to infinity. And it does not appear that the function ever decreases as you view from left to right. It looks like it's always increasing. So as the x values are getting bigger, the y values are never getting smaller. So we would say that it's not applicable, or we could say none. But I like to address it so that you know that we're not leaving it blank. So kind of a brief analyzing of our functions. So you can kind of do this for everything. And this is why it's really important to play with the parent function toolkit and understand some of those basic graphs so that you can address these questions. So let's see, we'll finish off with a trig example. We always have to kind of pull trig back in to the front of our minds. They always pop up here and there. So we are looking at y equals -g of x. And I have to kind of relate to who is g of x. And so I remind myself that the parent, or the basic function, will be cosine x. So that would mean, if I were to rewrite this in terms of an actual function, I would have y equals negative cosine of x. And if I'm comparing this to example 1, I do not see any extra numbers being added or subtracted. So I know that there's not really a vertical or horizontal shift. So I have to kind of look at how is it different from the parent function. And the only thing I see is that we have a negative sign in front of the entire function. So that is an indication that we're going to have a reflection. And what we want to think about is it going to reflect about the x-axis or the y-axis? Now you can use your TI to help you answer that question if you're not sure, but kind of recognizing some patterns makes our lives a little easier so we don't have to keep bringing out the TI. It appears that when something is on the outside of your function and there's a negative sign being multiplied to it, it's actually going to reflect about the x-axis. So we could start off with graphing our parent function. And again, I'll do that in green just so I can be consistent with example 1. So our parent function, if you prefer, you could make an XY chart, maybe a little bit from trig. We kind of are looking at the scale that we have, and we realize that cosine x starts always at 1. It also ends, periodic functions, it ends in the same place for a period of 2 pi. And some of the patterns from graphing all those trig functions in trigonometry, we kind of learned that if it starts at 1, stops at 1, the midpoint, we're going to have a minimum. And then we're going to have the quarter points as crossing through the x-axis. Should be at pi over 2 and 3 pi over 2. If you want to continue that pattern along, we can kind of look at from negative 2 pi to 0. We can keep the same pattern from our midpoint, quarter points, and endpoints. So here we have our y equals cosine x, and sometimes it gets a little confusing, so I'll make it dotted just so that you have a reference and it doesn't stand out too much. So we really want to inspect our actual graph that we're trying to do. So that is actually g of x equals cosine x on a period of negative 2 pi to 2 pi. If we want to talk about reflecting, this is where the points come in handy. Reflecting about the x-axis, remember, if we're looking at the x-axis and you do a reflection, any point below the x-axis reflects the same distance above the x-axis. So I'm looking at these two minimums and I'm going to redraw them over here. And anyone above the x-axis is going to reflect the same distance below the x-axis. So I'm looking at the two edges, or 3, I should say. And if you're on the x-axis, you're not really doing any reflecting. So we have, I'll keep them the same, I'll mark them. So if I were to connect those points in the same manner, it appears that we're going to have the cosine graph reflected about the x-axis. We do the best that we can. And I can label that so that we have that. So y equals negative g of x, or if you want to relate it to the actual function, that is okay. So now that we have a good idea, we could also use our RTI to check as we're starting off. We remember that the domain, and we can actually just eye it over here, appears that there's nothing happening. We have a periodic function. The domain is negative infinity to positive infinity. There's no asymptotes or holes in cosines. And the range of a cosine function, it's kind of stuck between -1 and +1. So that's where our trig comes in. And I know -1 and +1's included, so I make sure I have those brackets. Now you can play with analytical ways to speak about the cosine function. If you want to check with plugging in negative x for x like we did in section 1.1, feel free. But we can see what we've graphed in blue. It does appear, if you fold it along the y-axis, we do have symmetry. So I can actually address that right now. There's symmetry about the y-axis. And symmetry and even, odd, or neither are related. So if we are symmetric about the y-axis, we are an even function. Now the increasing decreasing part, kind of interesting as you're looking at it's making a wave. So there are intervals of increase and decrease. So if I were to describe the increase or decrease, I'll do it for one period and then we'll go from here. So let's look for on one period. Remember the period of this particular cosine function, it would be from 0 to 2 pi. Okay, so that's not the interval of increase. I just want to make sure that we're addressing that for this. If we're looking on one period from 0 to 2 pi, I'll highlight that. it appears that your function is increasing from 0 to pi. So I'll write that out. And when I'm looking at it, and we'll kind of inspect this a little bit more when we get to chapter 3, the function's not increasing or decreasing when you are at your max and your min kind of a level. And we'll relate that later. It's very important. But we'll kind of see we're not including 0 or pi. But for every x value in between, as your x values get larger, your y values get larger. So we are increasing on 0 to pi from that particular period. And also, if we are speaking about the decrease, if we're also just describing it with one period, 0 to 2 pi. The decrease would happen from pi to 2 pi. So if we kind of inspect what our function is doing, I think I'll highlight that in turquoise just so that we can see. Yeah, it turned green. But for every x value in between pi and 2 pi, as the x values get bigger, the y values start decreasing. They get smaller. So this is kind of what we're describing. And if we continue this, since we are a periodic function here, we're kind of looking at odd multiples of pi and even multiples of pi. So you could describe it, and we're not going to spend too much time with this, but if we keep repeating this process, deciding when are we decreasing or increasing, we're going to see all these intervals can be described as unions. So I can play with this. I'm going to leave it as this just to make your lives a little easier. Maybe I'll just explain it in English, and we can talk about explanation later. It's not too important for the rest of the class. We can definitely do this with calculus a little bit better. So we're looking at odd multiples of pi. And with, and I won't use and because sometimes that gets confused with union intersection. So I'm just going to write that in English. And then we also have ourselves even multiples of pi. So let's leave it at that. And at the most part, if I ask for intervals of increase and decrease, which I don't think I will until we get to chapter 3. We have a better way of describing this. But you could if this is a trig function or a periodic function, you would be safe if I asked for something on one period. It's a little bit nicer to describe. So hope that kind of helps you out. I didn't want to throw anything too crazy into the mix. But please remember that you want to go over your parent function toolkit and be able to describe most of these. With the trig functions, and we're talking about increase and decrease, it's okay if you're looking at a period of one period or 2 periods if you would like to. But please remember that we hold you responsible for these problems from our pre-calc. So go through them, and if you kind of get the idea of this, it'll give us a little bit of a nice preparation for the next section.